Alright, let's get started. So this is the last kind of force which I am going to introduce. This is very similar to the friction concept, but when the objects move in the fluids mean air or gases or liquids. So if when the objects are moving in the fluids, they experience the frictional force like the solids do. When there is motion related to two objects or solids moving with each other, that is called the kinetic friction. But when it comes to the fluids, it is called the drag force. Drag force always acts on any object which is moving through a fluid. It could be anything like small spores, dust particle in the air. You have the water droplets in the air, they experience the drag force. You jump off with a parachute opens, there is constantly a drag force acting on you, and the parachute also produces a force, a greater drag force on you so that you could slow down. So all the objects which move through the fluid, they experience a frictional force which is defined as the drag force. It is represented as Fd, d for the drag. It is a force just like other forces, other frictional forces. It tries to oppose the motion. So it's going to be in the opposite direction of the motion of the object. So if the object is moving downward, the drag force will be acting upward. So if you have a water droplet and it should move down through the air due to its weight, even though it's very light, but it still moves down. It does have a weight. If you're talking about big droplets, it's going to fall down because of its weight. However, at the same time, there would be, due to its surface exposed to the air, it will experience a drag force which will be in upward direction. Okay, you put some grains inside the water, they experience drag force in opposite direction of their motion. If the both forces are equal, what should happen? It should either stay still or it should move with the uniform speed. We all understand that it will not accelerate. It will only accelerate if either mg is greater than the drag force, upward force. It will move down. If the drag force is greater, then it would be floating. The drag force does depend on the shapes of the object, size of the objects, the quality or the type of the object, what it is made up of. There are two kinds of objects that experience the drag force at the microscopic objects, like it's dust particle that we cannot see, small spores, some viruses in a sample, those kind of things, you can treat them as the microscopic objects, which are very small. We cannot see them with the naked eye. So in that case, the drag force would vary, or it seems to vary with the speed of the object through the fluid. And they are directly proportional to each other. It's not a linear, it is a linear relationship between force and speed. The faster the object goes, the greater would be the drag force acting on it. And there is no power involved. They both are in linear relationship when we are talking about very small objects. Now, how small and how big the force can be, we can look at one example. I can write it as Fd equal to BV, where this constant depend on the size, shape, or the characteristic of the object we are talking about, like if it's a spherical droplet, or you're talking about something really huge, big balloon, drag force on a big balloon. Also the characteristics of the fluid. Why on fluid? Because if the fluid is very thick, like very dense, it's going to put more drag force, more upward force on the object, and that is going to make the object going very slowly through the fluid. Now, how small and how big this force can be? Let's look at an example. If there is a spore which has a radius of, when we will talk about the microscopic object, we are going to talk about very small distances. R is equal to 0.02 millimeter. If it is moving, so this is the radius is just given to estimate the size of it. We can go ahead, figure out the volume of the spore or the surface area of the spore, because that is going to affect this B value. But if B value, if it is known, like as 3.8 10 to the negative 7 Newton into second per meter. Now these values, they can be measured experimentally by using different sizes, different type of material. So these values can be found. So we already know some of the B values for some of the materials or commonly known materials. Newtons into second or meter. If it's moving with a speed of 5 times 10 to the negative 5, very slowly, the drag force will be equal to, if you multiply them both, you're going to get some number around negative 11 Newton. Now, even though if we in the real world this force is really small, but compared to the weight of this spore, this force is going to be good enough to make a difference to the overall or net force or the acceleration of the spores in the water. Okay, because it's comparable to the size. So it is comparable to the size of that object. Otherwise, if you're talking about a very huge object and going to get the force, drag force, which is about the same size on a large object, that's not going to make any difference for the weight of the object. But compared to the size, this should be making a difference. So, but at the same time, if the object is higher, the drag force would be greater too, because of the more exposed surface area. If the objects are really big, experimentally, large objects like cars, planes, big birds, dolphins swimming through the water, in those cases when we are talking about bigger objects, the drag force, it does depend on several factors. What do you think it could depend on? I mentioned a few initially when we defined B. It could depend on what? Surface area, yes. Speed, yes. The faster it moves, so the more force it will experience. Surface area, the greater the area is, greater will be the force, drag force on it. It also depends on the density of the material. Now this is not the density of the object, density of the fluid. So where air is more dense, it's going to exert more force on any object moving through it. So at higher altitude, the density could be lower, so is the drag force. At the lower altitudes, the density is greater, the drag force would be greater too. Fd is also proportional to the speed. However, it is observed experimentally that the drag force, it does not have a linear relationship with the speed here, but it has a square relationship. That means it increases with the square of the speed. If we put them together, proportional to A rho V square, proportionality sign goes away when you bring in the constant, half C A rho V square. That's the formula for drag force on big objects moving through the fluids. Big objects with some surface area, macroscopic object that you can see with the naked eyes. That is the constant. So when this, if it is solved, so this is beyond our scope that how we obtain this, but this can be obtained using the integrals. You will get this constant. But right now we just keep it there as like other constant that we know of, like mg, g is constant. Half c is a constant for any object moving, for any big object moving through the fluid. And this c depends on the shape of the object. And this half also comes from the experimental values. Okay, using different shapes, why the plane should look like the way it looks like, because based on its shape, the drag force will vary. Yes, yeah.
If you did this in the problem, would you have to give us the constant?
C, yes.
Okay, will we have to ever find it?
There is a table in your book. So when you prepare for this chapter, you will see a table given in your book where the drag force or C is given for different kind of object going through the air. Okay, some types of cars, special types of car, I think Camry is in there. So different types of car, what kind of drag force they experience, that is based on experimental work. Okay. Just like so most of the work related to friction, the values you see for the constants, these are not the constants which are determined in the labs. These are the constants which are like experimentally determined in different places. It's not like one universal constant. They are based on the experimental evidence. Okay, so if you want to know what is the mu s for if you move steel on the steel, so the experiment was performed using these two objects under different conditions, and then they came up with the value of mu s and mu k. This C has this half of C has the same way to find using the experimental results, using the experimental evidence. Half C has been placed with the drag force, and it will vary. This whole thing, this value of constant will vary with the shape of the object, size of the object, the way the plane is built or the car are built. So if you have something really wide exposed, so why the cars do not have a front like a flat surface? Why do they have a surface where the air can just pass over them easily? Like a nozzle, like they're going, because they are trying to decrease the friction around. Because if the surface is exposed like this, a big surface, it's going to block the air or fluid more. Okay, car will have to do more work, or more engine power will be used to work against that drag force. So in order to minimize it, the objects, they tend to move the object such way that they reduce the air friction or the fluid friction, where they are experiencing that drag force. When the drag force, when the objects are in fluid, they experience the gravity which is downward, and then they experience, for example, a water droplet. Is in the air, is moving through the air. Its weight is acting a spherical by default, we know that that droplet is going to be spherical, right? Because of the surface tension, when it is released after some time, it's going to have, it will have a spherical shape. So when it moves down, the weight force is acting downward, the drag force will be acting upward. And initially, when it is moving down, the weight force would be greater, but slowly, when it speeds up, right? When it speeds up, Fd increases. Is that right? Does it speed up when it's moving downward? When something is dropped, would that speed up? Yes, no? It accelerates, that means it...
But it should accelerate at a constant rate.
Yes, but it is speeding up, right? Everything which is dropped under the gravity is going to speed up, correct? So this droplet is going to speed up as it moves down. When it speeds up, what quantity depends on its speed? Mass cannot be changed. It's drag force on it, correct? How do we know that? Because they are directly proportional. It's right here. When the speed increases, drag force increases more. So when it's moving downward, it is going to speed up. When it speeds up, drag force increases. But how far it would go when it increases? It reaches to a point when Fd becomes equal to mg. What happens? It is already moving. You mean it will just come to rest in the air? Or it just continues wherever it is at the moment? Correct? It should continue with the uniform speed. So the net force on it, this is what we have been learning. Net force goes 0. There are two possibilities. If the object is at rest, it will stay at rest. If the object is moving with a uniform speed, it will keep moving with the uniform speed. So it will move with the uniform speed. Okay, because of inertia, it cannot just come to rest, right? Whatever speed it has gained, it will just maintain it. So by using this equation, we can come up with an equation. And half C rho A V square mg. V will be equal to 2 mg over C rho A square. Correct? How easy to find this equation? All you have to know is Fd. This velocity is called the terminal velocity. terminal velocity is the speed, is the uniform speed attained by the object. Terminal speed, final speed. Object under drag force, right? After that, it will move down with a uniform speed, and that would be its terminal speed. It will not accelerate anymore. Any example of something like that we know of? Something moving through the air? Something moving through the air. Sorry? Any object. Any object.
So this will stay the same no matter how big or how small the object is. This is always going to be.
Yes, this is for both. But remember, pay attention to that. This one is the formula for the large objects, right? So right now, this particular formula is indeed for macroscopic object. It's not for. If we use the drag force for the microscopic object, then the formula will be different. There will not be any square root involved. It really depends what kind of drag force you are using, because it does not increase with the speed as much as it increases for large objects. Parachute example. Why do we need parachutes? It does increase the drag force. How? It has more surface area. If we don't open the parachute, what will happen? Yeah. Loud noise, nobody would hear anything. So opening the parachute means more air trapped, more surface area exposed. That results in an external upward force. So in fact, the purpose of parachute is to reduce the time in which the drag force is increasing. So you would reach the terminal speed faster. Okay? Every object which is passing through the fluid will reach the terminal speed eventually. However, if the surface area is small, it may take really long time to attain that terminal speed. Before that, you can hit something. So parachute is used in order to reduce the time, to have enough drag force upward which could balance out the weight force downward. Okay, when they become equal, the person moves down with a uniform speed. So is drag force good or bad? Sorry? Depends on the situation. It's good or bad at the same time. When it is good, one example we just saw. If there was no drag force upward, or there was no way to control it, you could not attain there was no easy way for the object to levitate in the air, right, or in the fluids. The bad in a way that all the time the machines have to work against them. When we are driving the car, there is a constant force acting on the car which is acting backward. If we moving forward, the frictional forces are acting backward due to the air friction. We have been saying that the air friction, ignore the air friction, ignore the friction between the surfaces. But in the real world, these frictional forces are always there, okay, and we are at the cost of extra energy or power. We are trying to work against them. We still get the output that we need to get out of all the machines. We need to drive the car. We are going to drive the car, but at the expense of some energy, there is always some work against those frictional forces. So they can be good or bad, and they are there. That ends the chapter here. There is another topic, so where those who open their books, they know, they might know or they might see there is a topic, stress and strain at the end. Okay, I'm not going to touch it at the moment. Okay, I will hold on. I would cover it later with another chapter. Okay, so when you prepare for the test, you don't have to go through that. I'm going to start next chapter, centripetal force. That would be the part of your next test. Not this coming week. The week after that. So I think I would need only three lectures to finish it. And once I'm finished, we will have a test. It's already late for the test because we took too much time for the first test twice. So, and that's not going to happen again. There will just be one test and that's it. Because there is not much time left. All right. Chapter number 6. Circular motion. What comes to your mind when you think about the circular motion? A center, a radius, right? The quantity which are involved in the circular motion, total distance covered along the arc, the radius of that circular path, are you familiar with this picture from maths? So when the radius of the circular path is r, what would be the distance covered by the point? Or arc length, what would that be equal to? Arc length is the distance covered by a point from here to here. So this arc length or the distance covered can be given as hello? That's math. If we know that how much it has moved from one position to another position, and we know the angular displacement, we know r, what do we do with these two? Multiply them. S is equal to r theta. That's a math formula. Maybe I don't believe you had seen them in different symbols, because theta is always theta. If S is equal to R, that means that the total distance covered along the arc is equal to the radius, then theta is equal to 1 radian. That's a unit of angle defined in terms of radian. If there is one complete rotation, S is equal to R theta. If there is one complete rotation, the total distance covered will be 2 pi r theta. R gets cancelled. Theta is equal to 2 pi radians. Now these are not new things. You have seen them before. I'm just introducing them again in terms of radians in degrees. Theta is 360 degrees, 2 pi radians. 1 radian would be equal to 360 degrees divided by 2 pi. That's the relationship of radians and degrees. That is approximately equal to 57 degrees. If there is half rotation, what is pi equal to? Pi is equal to 180. Pi radians is equal to 180, right? Pi by 2 radians is equal to 90 degrees. If there are multiple rotations over this circular path, let's say 3.2 times 10 to the 2 revolutions per minute. That means it went over this circular path, which you don't see very clearly here, but that is the circular path with radius r. If it goes over that path with this many revolutions, revolution means one complete cycle per minute. This is defined as the angular velocity. We can convert this angular velocity radians, 2 pi radians divided by 1 minute. Minute can further be converted into seconds. 1 minute over 60 seconds. You multiply them, you will get some answer, 33.5 radians per second. So whenever we will talk about the rotational speed of the object on a circular path, so this quantity here, that defines the rotational or angular velocity of the object. Angular velocity. Now, this is something that I defined even before defining the angular velocity. Angular velocity, when the theta changes to a final position from some initial position over the time interval or delta theta over delta t. This is defined as angular velocity omega. Rate of change of angular displacement. Is defined as angular velocity. It is represented as omega. Omega is delta theta over delta t. Does omega remind you of anything that you have seen before? Any similarities with the straight line motion? Yes, so when the object is moving in a straight line, then velocity is equal to delta displacement over time, the total change in position over time. Here, since it's in the circular rotation, it's a circular path, our object is rotating, the angle is changing, angular displacement is changing. So we have replaced the linear displacement that we know of already from the linear motion by theta. Time is still the same. So the theta is playing the same role as it did previously for the linear motion or the motion in the straight line. Omega can have a positive. When was velocity positive or negative? It depends on the direction. When it is positive, positive x-axis. If it's along negative x-axis, it's going to be negative. Yes.
Are we exclusively working in radians in this, or are we still using degrees or stuff like that?
Radians. Yes. So where you will see all the numbers, the answers are going to be in radians. And so that's our SI units that we are going to follow for the angular velocities or speed here. We will keep our velocity in radians like we kept our velocity in meter per second, correct? Radian is our SI unit or fundamental unit for the angular displacement. So we will always use the angular displacement in radians. Omega can be positive and negative too. But it's positive and negative based on not motion in any direction, but based on its circular motion. If it is clockwise, it's negative, omega negative. If it is counterclockwise, omega positive. Okay, so see the way we define them, they are changing. Now the clockwise has come here. We have to discuss the clockwise motion and the counterclockwise because it's circular motion. It's not in any direction, positive or negative, upward or downward, but instead it is going to be in the circular path. If the object is rotating this way, where do you think the direction of omega is? Say it again.
Would it be positive?
True? Agree? If it changes its direction, Still positive? Another way to find that is the right hand rule. You turn your fingers in the direction of motion, curl them around, your thumb points towards the direction of omega. Okay, so if it is counterclockwise, that means my finger's gonna go up. Make sense? Wake up, Samantha. The fingers will go up. When they turn up, the thumb points towards omega. Or if you change the direction, if it is going clockwise and I turn my finger, so I always use my right hand to figure that out. So, but my right hand has to move accordingly so that I can turn it. Okay, because my hand cannot go backward. So in order to get the fingers along this direction, I have to turn my hand itself. So counterclockwise or clockwise. So that's another way to know about the direction. One way is if you can look at it, if it's counterclockwise, if you can look at it and tell that it's a counterclockwise, the direction should be this way, yes, sure. But if you cannot tell, then right hand rule could be one way to figure that out. The units of omega is radians per second. That's our fundamental unit for it, and we will always keep our number in the form of radians per second. For any instant, the value of omega is called instantaneous. When time is so small, then delta theta over delta t, that becomes equal to the instantaneous value. So value of omega at any instant. Now, as long as the object is moving or it's doing equal angular displacement over equal time interval, there is no acceleration. But when the omega changes, if it is speeding up or slowing down, if omega changes from one value to another, we call it that it has some acceleration. This is called angular acceleration. That is represented as alpha. Its role in the rotational motion is same as A in our linear motion, or delta omega over delta t. Just like our motion in the straight line, we always consider alpha as constant. We will consider alpha as constant here too for most of the cases. Constant acceleration. Because if the acceleration varies, we cannot apply the kinematics equation like we can using the constant acceleration. If we have the alpha changing, then we will have to involve the calculus in it in order to solve for velocities and the displacement. The equation of kinematics, they change accordingly. You will have omega f equal to omega I plus same kinematic equation and rotational equivalence. Delta theta is, theta f is equal to theta I plus omega I t plus half alpha t square omega f square plus 2 alpha delta theta. What is omega f? Final angular velocity, omega I, initial angular velocity, alpha is the angular acceleration. If the velocity is constant, alpha is 0, this part is set to 0. Final position, angular position, initial angular position, initial angular velocity, time, and angular acceleration. Okay, these are exactly the same with no changes other than the symbols that we have used. Omega, so V has been replaced by omega, A has been replaced by alpha, and X or Y has been replaced by theta. These are their rotational equivalents, but the equations, they remain the same.
So
Yes.
we would consider alpha as constant at 0 always?
No, constant, not 0.
So constant acceleration was 0.
Constant acceleration is not 0. Constant velocity or speed is 0 acceleration. But constant acceleration does not mean that the acceleration is 0. Okay? That simply means that velocity will always change by the same value over the equal interval. Okay? So when you say the word 9.8 meter per second square, you are actually telling me every time the velocity goes up by 9.8 meter per second, every second. That's what makes it 9.8 meter per second square. Constant acceleration means it is there. Velocity is changing. It's either speeding up or slowing down, but at a constant rate. Okay, when the variable acceleration comes into play, then you cannot simply use this formula. You will have to have some calculus involved in it. Okay. I am going to stop here. We'll start with the linear speed and the rotational motion. Also keep in mind, we still have one more quiz to go for the tension.